So that thermal equilibrium really is a dynamic equilibrium because heat really is moving back and forth between the two water containers. And just like with my thumb, if I died, the heat in my body would be lost to the environment, and we'd reach a point where my body temperature was the same as that of the environment. The environment actually would increase in temperature a tiny bit, but it's huge, so you can't really notice that part. And my body would come to thermal equilibrium. I would cool off until I was the temperature of my environment. So we can talk about various types of things where we can assign the equilibrium word or something like it. One of them is a static equilibrium. In a static equilibrium, not only does nothing change, the states stay the same, but in fact, nothing is changing, nothing is happening. You got two rocks sitting next to each other. They're absolutely stable, nothing's happening. What we've been looking at so far, however, are dynamic equilibria and steady states. The difference between a dynamic equilibrium and a steady state has to do with whether or not energy is required to maintain the system. So in a dynamic equilibrium, what you've got is a system that is something that's constantly happening. The different chemicals are constantly being shifted from the reactants to the products and back to the products. But overall, within the system, there's no change. So the concentration of the reactants and the concentration of the products is remaining the same, despite the fact that reactants are constantly converted into products and back again. Now, a steady state is a system where you've got things happening and you're not getting any change, but it requires energy to maintain the system in that way. And that's the example with my thumb, where you've got this heat gradient, this thermal gradient, and it's not changing. So it's like an equilibrium. In fact, heat's constantly being given off from me, so it's kind of like a dynamic equilibrium. But it isn't really an equilibrium. It's a steady state, because the only way that system's staying that way is because energy is constantly being put into my thumb, the heat from my body, which is then being lost. Mowing one's lawn. Presumably, I thought of this while I was mowing my lawn. So lawns want to grow, and we, for some reason, want to keep our lawns from growing. And so we're out there with our mowers cutting back our lawns. And as a consequence of that, our lawns are maintained at some relatively constant height. Okay? That height represents a steady state. In this case, the energy required to maintain the steady state is the energy we're putting into mowing. If we stop putting it into mowing, then the system moves to its essentially stable point, which is with the grass as high as the grass wants to be. Now, it's more complicated than that because grass requires energy to grow, but we're ignoring that part of it. And a lot of biology is you look at one aspect of it and you're not necessarily looking at all aspects of it. So in this case, we're looking at the height of the grass and not really asking how it is that the grass becomes high. But the grass has a propensity to grow, and we don't want it to grow. We want to maintain it at some relatively short height, so we're constantly out there mowing. And so that represents a steady state. Something's happening, the grass is constantly growing, and we're out there mowing, but ideally, so as far as we're concerned, the system is staying the same. The grass is being maintained at something close to a constant height. When we're heating our house, or for that matter, cooling our house, but this is with heat as an example. So we've got a furnace, and the furnace heats the house, and we've got it set up so we have feedback, negative feedback going on. When the house gets high enough, so we've got the furnace on, we get a gain in heat, the temperature of the house goes up, that's supposed to be a thermometer. When it gets hot enough, the furnace turns off, and the heat moves out of the house, goes through cracks, it radiates from the house. It's impossible to keep the heat in the house forever. So the temperature goes down, and we have a thermostat, and that thermostat says, oh, the temperature's gone down, and turns the furnace back on again. So we are maintaining our house at more or less the same temperature, But it's not a dynamic equilibrium because, in fact, it takes an input of energy to do this. And here it's quite obvious what that input of energy is, right? We're either burning electricity or burning natural gas or burning oil or burning coal or burning wood. Lots of burning going on. And that burning is really converting, actually, something that we can call potential energy into heat energy to keep our house warm. That has something to do with steady states. So in the text, I talk about the production and the loss of VW beetles. I don't know why I came up with that example. It has something to do with what the world was like when I was growing up, I'm sure. So VW beetles were made from, I don't know, 1940 something, or maybe even earlier than that. I think the last one was made in the early 80s in Brazil or something like that. But all through my youth, there were lots of these cars on the road. And so you can think of VW beetle production as a steady state, particularly if it lasted long enough. So if you had a constant rate of production of these cars, people would be buying these cars, and they'd be using the cars, and the cars would wear out. And if this went on for long enough, then the number of these cars on the road would be pretty much the same. As fast as the cars were made and put on the road, there'd be old ones retiring. It didn't work out quite this way because the number of VW beetles that were produced were increased over time. But if it went on long enough with a constant rate, you'd be making these VW beetles as fast as you'd be losing these VW beetles. And this is, in fact, a steady state because it takes energy to make a car. And you can think about all sorts of things. Any time where something is lost as fast as it's made, and really just about everything you buy that's disposable, and even things that you buy that aren't disposable, are being made as fast as they're lost. Because except for the fact that our populations are getting bigger, we're constantly bringing stuff into the house, and we're constantly taking trash out of the house. I mean, think of your refrigerator. How do you stock your refrigerator? You're constantly putting food in, and you're constantly removing food. That's a steady state. It takes energy to maintain that. You have to drive to the store. You have to spend your money. Somebody had to produce the food, et cetera, et cetera, et cetera. At some point, VW beetles stopped being made. And so they, at that point, just continued to decline, just like they had been all along, but you couldn't tell because they were being made as fast as they were declining. But once they were no longer being made, then they started declining. And what's this part of the curve? Well, at some point, people said, wait a minute, these things are kind of cool. I remember when I was a kid and I had a VW Beetle and I wish I had one now. And so collectors started buying these and they became more valuable and they stopped declining in number as fast. Maybe they're not used as much on the road, but there are a lot of VW Beetles sitting in people's garages out there. And so in a sense, we didn't treat our VW Beetles like Ferraris when they were abundant and cheap. But once they were no longer abundant and cheap and actually had some worth to people, people started treating them better. And so the rate of decline changed. So this story is basically a story based upon thinking of the world in terms of chemical equilibrium. I'm not using equations to do it. It's just that things are coming in as fast as they're going out, or maybe they're coming in faster, in which case the line's going up. Or maybe they're going out faster than they're coming in which case the line is going down. Maybe we've changed the rate at which something's happening, in which case the abundance curve is changing in its slope. So when you're looking at chemical equilibrium strictly, what you have are rate constants, one describing how fast things are moving on a per capita basis in one direction, and the other describing how fast things are moving in the other direction. I've drawn these arrows, a big one and a small one, to say that the propensity is to move much faster from B to A than from A to B, but that's on a per capita basis. So for any one B that's out there, its likelihood of turning into A is high. For any A out there, its likelihood of turning to B is actually relatively low. So when you've got a rate going from one thing to another thing that's high, but the reverse reaction is low, what's going to happen? You're going to accumulate the thing that that there's a higher potential to be to accumulate, to be turned into. So B is turning into A and A is accumulating. But there's some potential for A to turn into B, and once you have enough A around on a per capita basis, even though the likelihood of A turning into B is low, you reach a point where, in fact, you're having the production of B equal the production of A. Because you have so much A around that even though A is pretty pathetic at turning into B, you've got lots still that's turning into B. And so at this point where you have this balance in not necessarily the rate at which on a per capita basis something turns into something else, but the overall reaction, as fast as A is turning into B, B is turning into A, are equal, that's chemical equilibrium. And I draw it this way, first of all, to make you realize that you don't have to think of everything as being the forward reaction. Reverse reactions can be important too. But also to give you this idea that at the point of equilibrium, it doesn't mean that the concentration of A and B are the same. It doesn't mean the size of this letter and that letter are equal. It really depends on the rate constants. If A is more stable than B, you're going to have a lot more A, but if you've got a reverse reaction going on, you're still going to have some B, and everything's going to work itself out until you reach a point where you have enough A that the rate at which the reaction is going in this direction is equal to the rate it's going in that direction. That's chemical equilibrium. And then I have this long story that I go through in the book where I talk about people in rooms at parties, and that might be the equilibrium point, but if they get thirsty and there's drink in one room and food in the other room, their likelihood of going into the room that has the drink is suddenly going to become much higher, and that's going to change the equilibrium point. And then they're in that room with the drink, and they get hungry, but the food's in the other room, so suddenly they go back again, and they're going back and forth. And you could describe pretty much how many people are going to be in these individual rooms based upon whether they're very thirsty or very hungry. If you add a lot of salt to, you play a prank and add a lot of salt to the food, you're suddenly going to have a lot more people in the room where they're thirsty. And so you can establish new equilibria. Here it's showing that it doesn't matter how many people there are, you're going to have the same essentially ratio of individuals between the two rooms. And I've illustrated it like this. So this is people who could be thirsty and therefore going to that room, or could be hungry and therefore going back again. But then what I've done is I've put the Super Bowl, or something equivalent, in this room, and they don't know about it in this room. But they're in this room, and suddenly they were hungry, they went into this room, or they arrived at the party, let's say the door's there, and they immediately went to eat some food, and somebody, as a joke, put salt in the food, and so it's really salty, and then they're like, oh man, I'm thirsty, where are the drinks? Oh, the drinks are in this room. And they go into this room, and they grab their drink, and they're like, oh man, the Super Bowl's on, right? And so everybody at the party's going to end up in this room to the extent that room can hold everybody. And they're going to move to that room, if they don't otherwise know about the game, as fast as they become thirsty. That's going to determine how fast they go here. Once they're here, they're in there. But they're not going to know about it till they're here, and that rate constant is determining how fast they get into that room. So thinking about things in terms of chemical equilibrium. I was once fishing with a friend of mine who said, you can think about just about everything as a model, can't you? Because he was telling me how it really doesn't matter. The fish aren't attracted. This is salmon fishing. They're not attracted to a bait or anything. It's just having the hook in the right place where the fish are. And I was like, oh, well, there's some density of fish, and there'll be a density of hooks. And he didn't think that was the way to think about fishing.